Welcome. So the topic we'll be discussing in this lecture is we'll start discussing trees. Okay. As per the handout, there is 9 to 12 lectures. It should be searching and sorting. But I'm planning to teach this sometimes later. Okay. After discussing trees and binary trees, sometime later. Okay. The reason is being this is a proper flow. Whatever we are going, stack, queues, linked list, trees will go in that flow. And there are two reasons. That is one reason. The another reason is to some extent you might be already introduced to searching and sorting in your because you have involved in a lot of programming so far. So so of course it is not at all possible without searching and sorting. So so of course there are different searching algorithms which works in different ways, but you are introduced to the concept of searching and sorting. So at this point of time, I don't want to spend much time on this. So we shall move to the next topic, which is trees. Okay. So from today's class, we'll start discussing trees and the related topics. Okay. And it is actually a huge topic. See, you can see trees and binary tree as per handout. It is 5 lectures, and binary search tree, B plus tree, red flag tree, AVL tree, all these things. It is around 11 lectures. Okay, no, 11 or 12 lectures, which means next 15 to 20 lectures we'll be discussing this. Okay, right? Fine. So, uh, so the last class we have discussed about uh, circular linked list, simply circular linked list, right? So I hope we have also discussed a lot about linked list. We have discussed singly linked list, doubly linked list, and simply circular linked list. Now, the one thing that is pending is doubly circular linked list. Okay, doubly circular linked list. But I want you to study that by yourself. Okay, because I think it is almost it will be like repetition. Okay, so the idea I will give in a singly circular linked list. What happened? The last node's next pointer will point to the first node. Okay, in a doubly circular linked list, the last node's next pointer will point to the first node, and the first node's previous pointer will point to the last node. Okay, and and in a doubly circular linked list, if there is only one node, if there is only one node, then that node's next pointer will point to itself. Okay, because that is the last node. So that node's next should point to the first node. So that itself is the first node, so it is pointing to itself. Okay, and and the first there is only one node. Okay, so that node's previous pointer will also point to itself, because the first node's previous pointer should point to the last node. So there is only one node. So this itself is the last node. So this node's previous pointer will point to itself. Okay. So with this understanding, you should be able to implement doubly circular linked list, right? Adding nodes to a doubly circular linked list, inserting node to a doubly circular linked list after a specific node, or searching something whether a particular node exists or not, or whatever it may be, displaying the contents of a doubly circular linked list, counting the number of nodes, all these things I want you to implement by yourself. Okay, so so whatever the next quiz or test, whatever we have, there may be questions from doubly circular linked list also, but I leave this as a homework or an exercise. Okay, which you should do by yourself, right? Okay, so let us start with trees now. Fine. Okay. Yeah. Okay, so what is a tree? See, basically tree is a data structure. Tree is one type of data structure which used to represent hierarchical information. Tree is a data structure which is used to represent hierarchical data. Okay, see there are many hierarchy. There are if you see most of the data, uh, some of the data they may be hierarchical in nature. So such data can be better represented using trees rather than any other data structure. Okay. So one of the hierarchical thing is you can say that the what do you call your the details of your ancestors. Okay, maybe so you are the child. Who is your father? Who is your father's father? Okay, that is your grandfather. Who is your grandfather's father? Okay, that is a human inheritance. The human biological tree is a hierarchical in nature. Okay, so similarly, if you see, for example, there are many real-time data which are actually hierarchical in nature. For example, say for example, if you see what you call the generations of computers itself, if you take the first generation of computers, it used vacuum tubes. Okay, so that we can call it as the root. Okay, or the highest level of ancestor. Okay, the second generation of computer, which is of course derived from the first generation of computers. Okay, they used transistors, which is one advancement. Okay, so but actually second generation is 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 developed from first generation. Okay, then third generation of computers it used ICs. Okay, integrated circuits, right? Third generation, right? And fourth generation computers it used something called as VLSI. Okay, so if you see the VLSI is actually it is actually an improved or a more advanced version of IC technology. Okay, and IC is a more advanced technology, advanced usage of transistors. Okay, and transistors were developed from vacuum tubes. Okay, so this is also hierarchical data. You cannot put all these data in same level. They are not in same level, right? So like this, there are different type of data. By nature itself, they are hierarchical. So to represent such data, tree is the correct way. Okay, or for example, if you take different flavors of Windows, right? The originally Microsoft released an operating system called as DOS, disk operating system, which is actually a command-oriented operating system. Then later in the year 1995, they released Windows 95, so which is the first graphical user interface operating system which is ever released by Microsoft. And then they released Windows 98. Okay, and then they released Windows 98. Okay, and then in the year 2000 they released uh, Windows XP. Okay, Windows XP they released, right? So on and so forth. The journey continues. Okay, and then in 2007 they introduced Windows 7, right? In 2010 they introduced Windows 10, right? This is also what this is also hierarchical uh, data. Okay, or if you take the processors, initially the first ever microprocessor built is called as 4004 processor. From this later another processor was built which is called as 8008. Okay, and then there is a processor called as 8086. 8086, these are the name of the processors. These are Pentium. Okay, Pentium series, initially they numbered like this. Okay, then 80286, 80386, like that the journey continues. 802, it's 286, 80286, these are name of the processors. 80386, after that they calling naming it as Pentium, Intel Pentium processors. Okay, after 80386 it is uh, I think Intel Pentium 1, Intel Pentium 2, Intel Pentium 3, like that they started naming. Okay, Intel, so I'll call it as P1, P2, P3. I think it went on up to P4, right? Right. After that, they started calling it as Intel Pentium dual core. Okay, dual core. all these things, right? So like this, in today's we are calling today's Pentium processor are called as what? Pentium Core i3, Core i5, Core i7, Core i8. So this is also what hierarchy. See, such a long hierarchy. So these hierarchical informations or better can be better captured by using trees. Okay, right? Or sometimes it may so happen that in Intel Pentium 3 it is one level. Okay, Intel Pentium 3 processor itself, there may be two types. There may be two types of Pentium 3 processors. Okay, one with an internal cache, one without an internal cache. Okay, or with Intel Pentium 3 itself, there may be two processors with different speeds. One may be working on 800 megahertz. Okay, one may be working on 800 megahertz, and another processor may be working on 700 megahertz. Okay, so this is also, if you see, this is also, this type of information also can be captured by using trees in a better way, right? So these are the, so like that there are innumerable data which can be better represented by using trees, right? So this is the reason why we are bothered about the tree data structure. Okay, so I think I have convinced enough you to justify the purpose of learning the data structure tree. Okay, fine. So this is an example tree, okay, which shows the nature of a hierarchical data. Normally, how a hierarchical data looks like. So you can see. So each thing we call it as node. So there is a node Dusty. There is a node Dusty. This node Dusty has two childrens. What are they? Honeybear and Brandy. Okay, and so this Honeybear has again two children. So okay, so these are Brunhild and Terry, and Brandy has two children. Okay, Coyote and Nugget. Okay, and and, and Brunhild has two children, Jill and Tansy. Okay, so so this is actually a hierarchical data. This is actually a hierarchical data which represents some information. Okay, so so here you can see there is one ancestral, one node which is the ancestor for everyone, and that node is called as root node. Okay, so every tree will have a root node. Every tree will have a root node. A root node is a node which does not have any other parent. Okay, this root node Dusty, it does not have any parent. Okay, and here you can see Dusty has two children, Honeybear and Bee Randy, and Bee Randy has again two children. Okay, and Honeybear has two children. Like that, the tree can grow up to any level, right? And it is not that it should have only two children. It can have any number of children. Okay, so the tree can, it is not limited to only two children. It can have any number of children. Okay, so this the node which does not have any parent node is called as the root node. Okay, and the node which does not have any child is called as leaf nodes. So you can see these are the leaf nodes: Jill, Tansy, Tweed, Zoe, Crocus. All these are nothing but leaf nodes. Okay, so this is how we can visualize the tree structure, right? Fine. So how could we define a tree? Okay, so a tree is a finite set of one or more nodes. A tree is a finite set of one or more nodes. So these are called as nodes. All these are nodes. Dusty is a node, Honeybear is a node, Terry is a node. Okay. So what the first line says, a tree is a finite set of one or more nodes. It means that if you want to say something as a tree, it should have at least one node or more than that. Okay, right? So there is a specially designated node called the root node. Always in a tree, there will be a specially designated node, and that node will be called as the root node. Okay. Always in a tree, there will be a specially designated node, and that node will be called as the root node. Okay. The remaining nodes, that is the node other than the root node. Okay, remaining nodes in the sense the nodes other than the root nodes can be partitioned into n subsets. Okay, can be partitioned into n disjoint subsets such that n is greater than 0, greater than or equal to 0. That is other than the root node, all the remaining nodes we form some disjoint sets. Okay, and n can be greater than or equal to 0. If n is equal to 0, then it means that the tree has only one node. Okay. If n is greater than 0, then it means that the tree has more than one nodes. Okay. So the remaining nodes in the tree can be partitioned into n disjoint sets. Okay. So not one set, n sets. Okay. Such that what are the disjoint sets? T1, T2, T3 up to Tn, where each Ti is a tree. Okay, where each Ti is a tree, or you can call subtree of the root node. Okay, where each Ti itself is a tree, or you can say that it is a subtree of the root node. Okay, what does it mean? What does it mean? So what this definition says in the sense, a tree should have minimum one node, or it can have more than one node. And in a tree, there will be a specially designated node which will be called as the root node. The nodes which other than the root nodes can be grouped into n disjoint sets. This n can be greater than or equal to 0. If n is equal to 0, then it means that there is no other nodes other than the root node. Okay, if n is equal to 0, then it means that there is no nodes other than the root node. If n is greater than 0, then these subsets can be labeled as T1, T2, T3, T4 up to Tn. Okay, where each of these is a tree. T1 is one tree, T2 is another tree, T3 is another tree, and up to Tn is another tree. Okay, where all these trees T1, T2, T3, T2 up to Tn, all these are subtrees of root. Okay, the meaning is, for example, if you see this tree, if you see this particular tree, the original diagram, here this is the root node. Here this is the root node. Okay. So if you go back to the definition and refer, the nodes other than the root node, the nodes other than the root nodes, the remaining nodes can be partitioned into n disjoint sets. N disjoint sets, where each of these sets is a tree. Okay, what does it mean? So here you can partition this into two disjoint set. This is one disjoint set. This is one disjoint set, which we can call it as T1. Okay. This is another disjoint set. This is another disjoint set, which we can call it as T2. T2. Okay. So you can say that T1 is one tree. You can now say that T1 is a tree, right? What is the root of T1? Honeybeer is the root. And what is its child? Brunhilde and Terry. And what is Brunhilde's children? Jill and Tansy, like that. Okay. And T2 is another tree. What is the root of T2? Brandy is the root of T2. Who are the child of Brandy? Coyote and Nugget. Okay. So like that. So now you can say that T1 itself is a tree, T2 itself is a tree. But you can also say that T1 is a subtree of Dusty. That is the root node. And T2 is also a subtree of Dusty. Right? So that is what this second line says. The remaining nodes is partitioned into n disjoint sets. Okay? T1 to Tn, each of these is a tree. We call T1 to Tn the subtrees of the root. Okay? Here in this case n is 2. In this case n is 2. So it is subdivided into two disjoint trees. Okay? Again, this is a recursive definition. Actually, this definition, whatever we are discussing, is a recursive definition. Again, if you take the subtree T1, this can be again divided into two subtrees. What are they? This is one subtree and this is another subtree. Again, this can be divided into two subtrees. This is one subtree and this is another subtree. Okay. So this you can call it as ST1 and this you can call it as ST2. Okay. Or you can call as we are calling the outer tree as T1, I am calling this as ST1. Okay. Subtree 1, subtree 2. Okay. So subtree, this is a subtree of honeybeer. This is the left subtree of honeybeer and this is the right subtree of honeybeer. Okay. Similarly, this can also be divided into two subtrees. This is one subtree, this is another subtree. Okay. So on and so forth. Until you reach the child node, you can do this. Similarly, for Brunhilde, you can say that this is one subtree. Even though there is only one node, still this is one subtree. This is another subtree. Okay. Right. So this is the subtree of say I will call it as SB T1. This is the subtree of Brunhilde A. Okay, this is one subtree of Brunhilde A. This is another subtree of Brunhilde A. Okay, right? So we cannot go further because Jill and Tansy they don't have any children. Okay, so this is how we define a tree, right? Fine. But there is another definition for tree. So let me uh, uh, so a tree also can be defined in such a way that a tree is a graph without any cycles. Okay, you can also say that a tree is a graph without any cycles. So then you may ask, what is a graph? Okay, then you may ask, what is a graph? Yeah, a graph is also a tree. Uh, sorry, a tree is a graph without cycle. Okay, but a uh, but a graph is something which can have cycles. A graph is something which can have cycles. Okay, so if something is a graph, then you cannot call it as a tree. Okay, say for example, there is a node A, there is a node B. Okay, B is the left child of A, C is the right child of A. There is another node D. Okay, there is another node D, right? There is another node D. So there is C has one child E. Okay, C has one child E. Now if I say that B is also one of the parent of E. Okay, now this is a graph. This is not a tree. Okay, this is a graph. This is not a tree. Okay, because a tree is a graph without cycle. Here you can see there is a cycle. A to C, C to E, E to B, again B to A. So here we are not mentioning any direction, so it is an undirected graph. So there is a cycle. If there is a cycle, we call it as either cycle or circuit. If there is a cycle or a circuit in a graph, then that graph cannot be called as a tree. Okay, right? So a tree is a graph without cycles. Okay? So for example, if there is a tree like this, A, B, and C, this is a tree, this is not a graph. This is a tree, this is not a graph. Okay, and in a tree all nodes should be connected. In a tree all nodes should be connected. For example, say this is a valid tree because there is no cycles. There is no cycles, so it is a valid tree. If there is another node here, say K, and K is here, say F is here, like this. Okay, then this is one tree. This you can call it as tree 1, and this you can call it as tree 2. Okay, but both of these you cannot call it as combinedly as a tree. Okay, because they are not connected. Okay, because they are not connected. Okay, so a tree is a connected graph without cycle. Okay, a tree is a connected graph without cycle. Okay, so it means all nodes should be connected, but it should not have any cycles. Okay, if there is a cycle, then you cannot call it as a tree. So this is another definition, because this is also one of the important definition, because you should be able to differentiate between a graph and a tree. Okay, right? Fine. So in our example, if there is any connections between any two nodes, for example, there is a, I am saying that this is connected, then it means that it will become a graph. The moment this connection is added, it will become a graph. No more it will be a tree. Okay. So a tree is simply putting, a tree is a graph without cycles. Okay. Fine. And another thing, if there are n edges in a tree, if there are n nodes in a tree, then there will be n minus 1 edges. Okay. For example, this tree you can see how many nodes are there? 3 nodes are there. How many edges? This is the edge. Edge is the points that is connecting two nodes. This is edge 1 and this is edge 2. So the number of nodes is 3, number of edges is 2. Okay. So if there are n nodes, then there will be n minus 1 edges. If there are n nodes, then there will be n minus 1 edges. Okay. For example, you can check this graph, this tree. This tree has how many nodes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 nodes are there. So how many edges it has? If you see, this is one edge. Dusty to honeybear is one edge. Dusty to brandy is another edge. This is two. Honeybear to brunel is another edge. This is another edge. Okay. Similarly, this is another edge. This is another edge. Okay. So this is another edge. This is another edge. This is another edge. This is another edge. And these are the two edges for CO. These are the two edges for nutjet. Okay. So now if you count, we already counted the number of nodes 15. Now you count the edges 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So if there are n nodes in a tree, then there will be exactly n minus 1 edges. Okay. So this is how we define a tree. Okay. So there are different definitions we have discussed. What? So a tree will have at least one node or more than one node, and all the remaining nodes in a tree can be partitioned into n disjoint sets from T1 to Tn, such that each of these is a tree. That is, we call T1, T2 up to Tn as a subtree of the root node, right? And a tree in terms of graph, how can you define a tree? A tree is a graph without cycles. A tree is a graph without cycles. And if a tree, and in a tree if there are n nodes, then there will be exactly n minus 1 edges, right? Okay. Then there are some of the terminologies are there. We shall discuss few terminologies about trees. Okay. So this is a tree. Here you can see the node A has 3 children, B, C and D, and B has 2 children, E and F, and C has 1 child, G, and D has 3 children, H, I and J, and E has 2 children, K and L. H has 1 children, which is M. Okay. Now if you see, now let us try to understand all these terminologies. Okay. Node, you know what is a node? Okay, the node is nothing but any vertex in a tree is called as the node. Okay, so A is a node, B is a node, C is a node, D is a node, all these are nodes. So how many nodes are there in this tree? If you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 nodes are there. Okay. Right. Then what is the next is, what is the degree of a node? So degree of a node is the number of subtrees a particular node is having. Right? Degree of a node represents the number of subtrees a particular node is having. Okay. So if you take node A, how many subtrees it has? It has 3 subtrees. B, this is one subtree. This is one subtree. This is another subtree. Okay. This is another subtree. So it has 3 subtrees. So the degree of a node is nothing but number of subtrees that particular node has. So node A has 3 subtrees, so its degree is 3. Right? What is the degree of node B? How many subtrees it has? It has, this is one subtree, this is another subtree. So it has, its degree is 2. Okay. What's the degree of C? How many subtrees it has? It has only one subtree, so its degree is 1. Right? How many subtrees node D has? It has 3 subtrees, 1, 2 and 3. So what is its degree? Its degree is 3. Okay. So on and so forth. Like that we calculate degrees. Okay. Degree of the root node, degree of the leaf node will be 0. For example, if you take E, it has how many subtrees? This is one subtree, this is another subtree. Okay. So its degree is nothing but 2. For F is a leaf node because it does not have any children. The node which does not have any children is called as leaf node. So it does not have any children. So its degree is what? 0. Okay. G is a leaf node, its degree is 0. H has only one subtree, so its degree is 1. I don't have any subtrees, so its degree is 0. J don't have any subtrees, its degree is 0. K don't have any subtrees, its degree is 0. L don't have any subtrees, its degree is also 0. Okay, fine. So already we defined a leaf node. A leaf node is a node which does not have any child. So such a node is called as leaf node. Leaf node is also called as terminal node. There is another name for leaf node which is called as terminal node. Okay. Then what is a non-terminal node? All nodes which are not terminal nodes are called as non-terminal nodes. That is, the nodes other than the leaf node will be called as non-terminal nodes. Okay. The nodes other than the leaf nodes will be called as non-terminal nodes. So in this graph, if you see what are the leaf nodes, K is a leaf node, L is a leaf node, M is a leaf node, F is a leaf node, G is a leaf node, I is a leaf node, J is a leaf node. These are the leaf nodes. Okay. So that means their degree is 0. For all leaf nodes, that they don't have any what you call subtree or children. So their degree will be 0. And they are called as terminal node. Okay. The nodes other than the leaf node are called as non-terminal nodes. The nodes other than the leaf node are called as non-terminal nodes. So which are the non-terminal nodes? E is a non-terminal node, H is a non-terminal node, B is a non-terminal node, C is a non-terminal node, D is a non-terminal node, and A is a non-terminal node. So these are the non-terminal nodes: A, B, C, D, E, and H. Okay, A, B, C, D, E, and H. These are the non-terminal nodes in this particular tree. Okay, right. And what is the parent? Okay, the node which is, if a node has some children, then that node is called as the parent node. So A is the parent of B, C, and D. B is the parent of E and F. C is the parent of G. D is the parent of H, I, and J. Okay. If a node has some child nodes, then that node is called as the parent node. Okay. And and the immediate descendants of a node will be called as child nodes. Okay. Immediate descendant of a node will be called as children. So the immediate descendant of A is what? B, C, and D. So B, C, and D are children of A. Similarly, the immediate descendant of B is E and F. So E and F are the children of B, like that. Okay. Sibling. What is sibling? The children of the same parent are called as sibling. The children of the same parent are called as sibling. So if you see here, what are B, C, and D has common parent. B, C, and D has same parent, that is A. So B, C, and D are nothing but sibling, right? Similarly, E and F has same parent, so it's a sibling. Can I call E and G as a sibling? No, they are not sibling because their parent are different. E's parent is B and G's parent is C. Okay, right? Okay. Then let us try to understand what is meant by degree of a tree. Previously we discussed degree of a node. The degree of a node is what? The degree of a node is equal to the degree of a node is nothing but number of subtrees a particular node has. That is called as the degree of a node. So we calculated the degree of each and every node. A's degree is 3, B's 2, C 1, so on and so forth. What is the degree of tree? So actually degree of tree is calculated from the degree of node. Okay. After calculating the degree of node for all the nodes, after calculating the degree of nodes for all the nodes, you identify the node with the maximum degree. You identify the node with the maximum degree. So in this tree, for all nodes, the degree is calculated. 0, 0, like this. You can see all these green things are nothing but degree. Okay. So for every node, the degree is calculated. So which is the node with the highest degree? So node A has highest degree, and what is that? 3. Okay. So the highest degree will be the degree of the tree. The highest degree of a tree, the highest degree of nodes of a tree will be the degree of a tree. Okay. Right. So in this case, node A has the highest degree, which is 3. So the degree of tree is also 3. Right. Fine. What is ancestor? Whatever the nodes which came, whatever the nodes which came in the path of the root node, when you travel upwards towards the tree, those nodes are called as ancestors. Okay, for example, if you take K, the ancestor of K is E is ancestor of K, B is also an ancestor of K, and A is also an ancestor of K. Okay, If you take L, again E is the ancestor, B is the ancestor, and A is the ancestor. If you take F, B is an ancestor, A is also an ancestor. If you take M, H is its ancestor, D is its ancestor, and A is its ancestor. Okay. So when you travel from the bottom of the tree towards the root, whatever the nodes which come on the way, all those nodes will be called as the ancestor of a particular node. Right. What is the level of a tree? What is the level of what is the level of a node? Okay. What is the level of a node? Right. So level is also called as level is also uh, level is also called as depth. Okay, in some other terminology, level is also called as depth. Okay, so there are two terms. Either you can call it as level or you can call it as depth. Okay, so if you see the level of the root node is 1. Level of the root node is 1. Okay, it is at first level, and these are the next level nodes. The immediate children of root node is at level 2. The immediate children of root node is at level 2. Okay. The grandchildren of level root node is at level 3. The grandchildren of root node is at level 3. Okay. Right. The and the next the children of the grandchildren are at level 4. Okay. So on it proceeds. Okay. So this is called as the level. So here we start the root node as level 1, next set of nodes as level 2, next as level 3, and next as level 4. Okay. But in some of the books they may call the level corresponding to root node as 0. Okay. In that case, this all these nodes will come under level 1, B, C, and D, and the next will come under level 2, E, F, G, H, I, J, and next will come under level 3. Okay. It all depends. It can vary. Okay. So when you are asked a question, probably you may be given that assume the root level, assume the root node as level 0. Okay. If the leveling starts from 0. Okay. If no such things were given, then by default you should assume that uh, the level of the root node is 1. Okay. By default you should assume that the level of the root node is 1. Fine. Okay. Then height of a tree. What is the height of a tree? So height of a tree uh, is actually it is a height of a tree is actually uh, from the whatever the node, the leaf node which is at the bottom level, and how many links are required to reach the root node. Okay, that is the height of the tree. Okay, for example, here the bottommost leaf is available at which level? 4th level. Okay, there is no more level below 4. Okay, there is no more level below 4. Okay, right. So from here, how many? I mean, what is the at what level the root node is available? Okay, that is called as the height of the tree. Fine. There is also here I'll be also using another website which I feel it is good enough. Okay, so let me share that also. Yeah. So this website here also will be referring these websites. Okay, Gate Vidyalay. I too want you to go through this website. Okay, all the starting from trees, I want you to go through this website and to practice all the problems given here. Okay, you may also get questions from here. So here also there are some terminologies and definitions for tree which I want to share. Okay, so here see the definition. A tree is a non-linear data structure which organizes data in a hierarchical structure. Okay. Yeah, this also you should remember, tree is a non-linear data structure. It's not a linear data structure. Okay. So far whatever we have discussed, they are linear data structure. Okay, but but uh, but tree is not a linear data structure. It is a non-linear data structure. Okay, right? It's not a linear data structure. It organizes data in a hierarchical structure, okay, and this is a recursive definition. A tree is a connected graph without any circuits or cycle, okay. In a graph, there can be, if in a graph there is only one path between a pair of vertices, then such a graph is called as a tree, okay. This is another definition of a tree. If in a graph there is only one path between every pair of vertices, then such a graph is called as a tree. For example, this left side one, this is not a tree, this is a graph, because here it's a cycle, okay. Whereas the right side one is a tree, okay. Right. Okay. So every tree is also a graph, okay, but every graph is not a tree, okay. So this graph, you can see the right side one, we can call this as a graph. This graph is a tree, but the left side graph is not a tree, okay. See the last definition, in a graph there is only one path between every pair of vertices, okay. So in a graph there is only one path between every pair of vertices. For example, you see this right side tree, A to E there is only one path. If you want to reach E, you have to go from A. If you want to reach E, then there is only one path, A to C and C to E. There is no other way. You cannot go to B and then you cannot come to E, okay. Similarly, you cannot come to C and then after coming to C, if you go to D, then you cannot reach to E, okay. Without reaching C, you cannot come to E. Are you getting? But if you see this left side graph, what happens? If I want to reach E, there are multiple paths available. I can go from A to C and C to E, or I can go from A to C, C to D and D to E, okay. So that is what the last definition says. If in a graph there is only one path available between every pair of vertices, then such a graph is actually a tree, okay. Right. So these are some of the properties of a tree. There is one and only one path between every pair of vertices in a tree, which is nothing but the last definition, okay. Which is nothing but the last definition of a tree. And a tree with n vertices has exactly n minus 1 edges, which I have already told. A tree with n vertices has exactly n minus 1 edges. A graph is a tree if and only if it is minimally connected, okay. Minimally connected means it does not have any cycle and all nodes are connected, okay. A graph is a tree if and only if it is minimally connected, okay. Any connected graph with n vertices and n minus 1 edges is a tree, okay. This property is similar to second property. If a tree has n vertices, and a tree will have n vertices and exactly n minus 1 edges, okay. So any connected graph with n vertices and n minus 1 edges is a tree, right. So these are some of the properties of the tree. Tree terminologies, these are the various terminologies, okay, some of which we have already discussed. If anything missed out, we'll see. So root, it's the special node which does not have any parent. That node is called as the root node. Edge is what? The link that is connecting between any two nodes, that is called as the edge. And what is a parent? The node which has a branch from it to any other node is called as a parent, okay. We discussed already. So if you see this particular tree, A is the parent of B and C, B is the parent of D, E and F, E is the parent of I and J, so on and so forth. Child, the node which is a descendant of some node, a node which is a descendant of some node is called as the child node. So B and C are a child of A, okay, D is the child of B, E is the child of B, like that. Okay. Siblings, node which belong to the same parent are called as siblings, okay. Node which belongs to the same parent are called as sibling. For example, B and C belong to the same parent, so they are sibling. D, E, F belong to the same parent, so they are sibling. G and H belong to the same parent, C, they are siblings. I and J belong to the same parent, they are siblings, okay. Degree. So degree of a node is the total number of subtree or children that the node has, okay. Subtrees, we can call it a subtree or children, okay. So the degree of A is 2 because it has 2 subtrees or 2 children. Degree of B is 3 because it has 3 subtrees or 3 children. Degree of C is 2, okay. Like that you can calculate the degree of all the nodes. And what is the degree of a tree? Degree of a tree is nothing but the whichever the node is having the highest degree, that will be the degree of the tree. Okay. So for example, in this graph, if you see here, all degrees are calculated. Degree of A is 1, B is 3. Okay. A is degree of A is 2 nodes. Okay. B is 3, C is 2, D is 0, no children. Okay. E is 2, F is 0, G is 1. Okay. H is 0, I is 0, J is 0. So what is the degree of this tree? Which node has the highest degree? Node B has the highest degree, and what is the degree value? 3. So the degree of the tree is 3. Okay, the degree of this particular tree is 3. Okay. Internal node. So internal node is nothing but a non-terminal node. Actually, we discussed what is non-terminal node. The node other than the leaf node are called as internal node or non-terminal node. Okay, leaf node is called as terminal node or external node. Okay, so so in this graph, if you see which are the terminal nodes, D, I, J, F, K, H. These are the terminal nodes. So these are not the internal nodes. Other than these, all other nodes are internal nodes. A, B, C, E, and G. All these are internal nodes. Even root node is also an internal node. Okay. All nodes other than the leaf nodes are internal nodes. What is a leaf node? The node which does not have any child is called as leaf node. Leaf node is also called as external nodes or terminal nodes. These are different terminology. Okay. So the nodes other than the leaf nodes are also called as internal nodes or non-terminal nodes. Okay, level. So already we have discussed level. So level is nothing but what? So previously in the slide we have discussed root is level 1. So generally it is level 1, level 2. Okay, but here they are calling as level 0. So different authors, they actually specify in different way. Okay, so as per our textbook, let us assume root as level 1, and the next the immediate descendants of root as level 2, and next as level 3, and next as level 4, right? What is the height? What is the height? The total number of edges that lies on the longest path from any leaf node to a particular node is called as the height of that node. Okay? The total number of the edges that lies on the longest path from any leaf node to a particular node is called as the height of the node. Okay? So height of the node in the sense the number of edges that lies on the longest path from leaf node from any leaf node to a particular node is called as the height of that particular node. Okay, that is, for example, if you take B, what is the height of B? You to identify the height of B, you have to go up to J. How many levels are there? 1, 2. So height of B is 2. Okay, height of H is 0 because there is nothing here, right? Height of A is 1, 2, 3. It is 3, right? Okay, that is from that particular node go up to the what do you call leaf node and then find the height. Okay, height of all leaf nodes are 0. Height of a tree is nothing but the height of the root node. Height of a tree is nothing but the height of the root node. So root node, how many edges it can pass through? 1, 2, 3 to reach the leaf node. To reach the leaf node in the longest path. Okay. So here you can also reach the reach the leaf node F, but that is not in the longest path. Longest path is I, J or K. So for reaching that you need how many? How many levels? 1, 2, 3. Okay. So that is called as the height of a node. Okay. So here the height of all the nodes are calculated. The height of the root node is nothing but the height of the tree. Okay. Okay. And then what is depth? What is depth? So the depth. So the depth is nothing but level. Okay. Depth and level are used interchangeably. Okay. Depth is nothing but level. So depth and level are used interchangeably. The total number of edges from the root node to a particular node is called as depth. Okay. So so in this case you can see as per this particular thing here root node is called as at depth 0. This is depth 1. This is depth 2, depth 3. Okay. As per the textbook, this is depth 1, this is depth 2, this is depth 3, and this is depth 4. Right? So subtree, in a tree each child uh, each child from a node forms a subtree. Okay, so what is the child of A? B is the child of A, so this entire thing is a subtree. What's the child of another child of A? C, so this entire thing is a subtree. Okay, again B's child, this E, this entire thing is a subtree. Even this D is also, you can call it a subtree, even though it has only one node. Okay, so subtree is nothing but the children of any node can be called as a subtree. Forest. What is a forest? A forest is a set of disjoint trees. Okay. In real life also, what is a forest? A forest is a collection of trees. Okay. So when you combine two or more trees, that is a forest. So this is one tree. This is another tree. So put together, it is called as a forest. Okay. So these are the various terminologies with respect to what you call trees. Okay. So right. So here uh, so as I have already said, height and what do you call the height of a tree is nothing but uh, height of a tree. What is height of the tree? How do you define the height of the tree? As per this, height of tree is defined as the total number of edges that lie on the longest path from any leaf node to a particular node is called as the height of the node. Height of a tree is the height of the root node. Okay, that is any longest path from the root from that particular leaf node to the root node. Okay, longest path from the leaf node to the root node is the height. So here longest path is either K or L or M. Okay. So again height as per that definition, the height should be 3, right? Here to here is 1, here to here is 2, here to here is 3. Okay, but here our height is 4, right? So it is again, it is something like in depth also we are calling this as depth or level. Okay, level is otherwise called as what? Depth. Okay, level is otherwise called as depth. Level is otherwise called as depth. So the root node we are calling it as level 1 or depth 1. This is at depth 2 or level 2. This is depth 3 and this is uh, depth 4 or level 4. Okay. Similarly, height also, what you can say is from uh, any particular node, how much from a given leaf node. Okay, from a given leaf node to reach a particular node, how many links you have to pass through plus 1, that is the height of a tree as per the textbook. Okay, for example, that is the height of that particular node. Okay, and the longest path from the leaf node to the root node, okay, plus 1 is the height of the tree. Okay. For example, if you want to identify height of C, what is the uh, height of this particular node C? Okay, so there is only, you can reach C only through one leaf node. Which leaf node? G. Okay, so to reach C, how many pass? Only one link. Okay, but to that you have to add one more, so that is 2. So 2 is the height of C, right? We're getting 2 is the height of C. Okay, but if you take B, to reach B, what is the longest path available? Either K or L. So it is 1, 2. 2 plus 1 is 3. 3 is the height of B. Okay. But if you take A, what is the height? It is 1, 2, 3. So 3 plus 1, that is 4. 4 is the height of what you call A. Okay. Right. So these are just different terminologies. Let us not much what you call bother of that. Okay. So but most of the time I think we'll use this level. Okay. So let us by default let us assume that unless and otherwise it is not specified, let us assume that root node comes in level 1. Okay. This is level 1 and next is level 2, next is level 3. Okay. But sometimes in the question if it is given, then you have to assume root node as level 0. Okay. Fine. Okay. So all these are whatever we have discussed, right? Okay. Next we will see like how to represent a tree. So how can so in programming, how will we represent the trees? So we need some data structure to represent tree. So how can we do that? Right? We need some data structures to represent trees. So what can be done? So there is one simplest way to represent which is called as list representation. Okay, there is a simplest way of representing which is called as list representation. So this particular tree can be represented using list representation, something like this. Okay, what does it mean? It means that the node A has three children, B, C and D. Okay, that is the meaning. Okay. And B has two children, E and F. Okay. And E has two children, K and L. Okay, right? So A has three children, B, C and D. B has two children, E and F. And E has two children, K and L. And C has one child, G. Okay, and D has three children, H, I and J. And H has one child, M. That's the meaning of this. Okay. So how to put it in words? That is, whenever something is represented inside a bracket, it means that is the child of that. Okay. So if you go from the innermost bracket, here in this case, let us come from left to right. So this is the innermost one. So K and L are nothing but the child of E. Okay. So this is again one level of bracket. Okay. This is one level of bracket. Okay. Then E and F are nothing but the child of B. Okay. So this is another level, E and F. It's another level. Okay. Again, if you come here, G is the child of C. So this is one level. Okay. Here if you see, M is the child of H. This is one level. Okay. H, I and J are child of D. This is another level. Okay. Then if you say B, C and D are the child of A, right? So this is a very basic way of representing using list, right? Okay, but performing operations or manipulating this list or how we will represent. I mean, representing by hands like this is fine, but in what form you will represent? Okay, so it is actually a question. So we need some data structure to represent. Okay, so this is one common thing you may think, that is we should need a data structure something like this. There should be a data part and there should be some link part, link 1, link 2, link 3, link 4 up to link n. But like this, how many links you should have? How many links you should have? So you should know in advance like how many links should be there, right? So how do we know all these things, right? So these are the questions we get when you think of representing this particular thing as a data structure. Okay, fine. So one of the easiest way or one of the uh, commonly suggested way to represent this is, so here the problem is what? Why can't we represent like link 1, link 2, link 3 means actually how many pointers we need that we cannot predict. Okay. Otherwise, even if you predict, the number of pointers may the number of pointers that you use may be more. Okay. For example, the number of pointers to be used can be limited to the degree of the tree. Okay. The number of pointers to be used can be limited by the degree of the tree. What is the degree of a tree? How will you define the degree of a tree? What is the degree of a node? The number of child a node has, that is its degree. The number of children a particular node has, or a number of subtrees a particular node has, that is the degree of that particular node. Okay. Degree of a tree is what? Uh, the num the maximum degree, the node with the highest degree. So that value will be the degree of the tree. Okay. So for this particular tree, we have already calculated the degree. What is the degree of tree? 3. So it means that there is no node with more than 3 children. It means there is no node with more than 3 children. Only root node has 3 children, other nodes don't have 3 children. Okay. So in that case, you can assure that it is enough to have a data structure something like this. It is enough to have a data structure something like this, which has one data part, and 2 and 3 pointers. It has one data part and 3 pointers. P1, these are pointers, P1, P2 and P3. Because there will not be any node with more than 3 pointers, right? So you may use all the 3 pointers for the root node. Okay, say this is the root node, this is root node A, this pointer 1 may point to B, pointer 1 may point to B, pointer 2 may point to C, pointer 3 may point to D. Okay. Again B can be represented like this. Again B can be represented with one data part and 3 pointers. Okay. 3 pointers P1, P2 and P3. But if you see B has only 2 children. So this is B. So here you will use only 2 pointers. Pointer 1 and pointer 2. Pointer 3 will point to null. Pointer 3 will point to null. Okay. Similarly, if you see C also you can represent using one data part and 3 pointers. But actually in C you will be using only one pointer. C's child is G. Remaining 2 pointers will point to null. Similarly for D, if you see there are 3 children, H, I and J. So all the 3 pointers will be using. Okay. D has 3 children, H, I and J. Okay. So on and so forth, this can be done. Okay. This will continue. That is, every node can be represented by using one data part and 3 pointers. Okay. But still, in this representation also, there are many pointers getting wasted. For example, in B, one pointer is you are wasting. In C, one pointer you are wasting. Like that, if you count overall, there will be many pointers which is getting wasted. So which is nothing but which you cannot call it as an effective usage of data structures. Okay. So we are thinking, is there any other way to represent this in an easier way, right? So there is one simple way to represent this. Okay. So that is okay. Let us stop here for this lecture. We will continue the remaining part next. Okay. So far what we have discussed is we have defined a tree. We have defined tree in several terms. We have just defined tree, what is a tree, and then we have defined tree in terms of graph, so on and so forth. And we have discussed several terminologies connected with trees, and also we have discussed like how to represent trees using list representation, and also we have discussed what are the challenges or complexities in representing a tree as a linked list by using data part and the pointer part. Okay, and what is the solution? How can we represent the trees in a with minimal data structure? That is what we have to sort it out. Fine, let us stop this lecture here. Thank you.